This is level 1 of the CFA program, the topic on quantitative methods, and the reading on common probability distributions. You might notice that every once in a while I will refer you to the actual reading. What I'm going to do now is refer you to one of the first handful of sentences in this reading, which is extremely well written, by the way. The sentence goes something like this. We cannot predict the future. Now, if there were a period at the end of that sentence, we'd probably just close up and move on to the next reading or move on with our lives. But there's a comma at the end of that sentence, and it goes something like this. We cannot predict the future, comma. However, comma, we can, as good financial analysts, make informed investment decisions using some estimate of a probability of an outcome. Now, of course, we're super familiar with probabilities. We deal with this every day. I'm guessing that you live your life kind of like I live my life. Wake up in the morning and you wonder, what's the probability that it's going to rain today? What's the probability that the dinner that I cook tonight is going to be well received by everybody in my family? Good financial analysts, however, ask questions like this. What is the probability that a board of directors is going to increase its dividend? What is the probability that cash flows are going to exceed some given number? What's the probability that dividend yield is going to be less than 2%? And as you look through these learning outcome statements, you'll notice that the words probability and distribution and random variables are rampant in almost every one of these. So we're going to talk about probability distributions in discrete and continuous form. We'll talk about a couple of guys who had some important contributions to the field of probability and statistics. And then look at the bottom there, a normal distribution. This is going to be super important for us going through, not just for the rest of level 1, but level 2 and level 3 and beyond our life as good financial analysts. And then, as I'm guessing you noticed, that there are lots and lots of learning outcome statements here, but still there's normally distributed random variables, how to standardize a random variable. And then somewhere after that third LOS on this slide, what we're going to do is kind of switch gears and ask ourselves, okay, we're understanding probability and normal distributions, but how can we get back to, what did I say just a few moments ago? Making informed investment decisions. And we're going to try to do that using things like shortfall risk and a couple kinds of ratios. And then we'll look at t distributions and chi-square distributions and f distributions. And then we'll end with a discussion on Monte Carlo simulation. All right, let's go ahead and start with that first LOS. Describe and define a probability distribution. All right, so let's go ahead and read that first bullet point together. Probability distribution of a random variable x is a graphical representation of the probabilities. All right, so there we have a die, and so we can roll it, right? And all we're going to do is get either a 1, a 2, a 3, a 4, a 5, a 6. And so each outcome is going to occur with a 1/6 probability. That's 16.7%. So if you kind of visualize a line going across the top of all those blue bars, you have equal probabilities of rolling any one of those 6 numbers. So that probability would be a straight line. Of course, this is, super simple, but those of you who are James Bond fans like I am, you might go back to that great movie Diamonds Are Forever, where Sean Connery goes to the craps table in Las Vegas. And of course, he's rolling 2 dice. And those of you who know how to play craps, you roll the dice and you can win or lose on that first roll. But then if you don't crap out, you get to roll the dice again. So what's going on there with that probability distribution? Instead of just 1, you now have 2. And then you have 2 rolls of 2 of these die. And so that probability distribution is probably not going to be a straight line. So what we need to do is start at the simple point with a straight line and then move on to where those probability distributions are not. A couple of good definitions. A discrete random variable can take on a finite number of outcomes. Look at some of the examples. We just talked about the rolling of a dice, number of CFA charter holders, number of mutual funds in the U.S., number of foul shots that Steph Curry makes in any basketball game, number of touchdown passes that Patrick Mahomes throws in any given game or a season. How about this one? Number of whiffs that Tiger Woods has on the tee box of major tournaments. Well, that's probably not a random variable because they're all zeros, right? So make sure that random variables, when you get to this question on the exam, that they are random. Continuous random variable, on the other hand, can take on an infinite number of outcomes. So notice we have bolded there, finite and infinite, as a distinguishing difference between discrete and continuous random variables. And so look at the example that we give. Clearly that you can have a rate of return of 6% or between 6 and 7%. And that might sound like it's discrete, but of course it could be 6.4, which is between 6 and 7. It could be 6.41 or 6.412 or 6.41 and a whole bunch of numbers. Those are all between 6 and 7. So there's that concept of infinity. And I'm guessing, given my age and your age differences, when I was in high school and college, this concept of infinity really was beyond my grasp. But those of you who are younger than I am, you had the benefit of seeing those great Toy Story movies, and so Buzz Lightyear, Infinity and Beyond. Maybe that's your reference point, and that's okay. That's a good reference point. So just think 6.41, and you can go out to a whole bunch of numbers. All right, how about a probability function? A lot of times in finance, we are interested in asking ourselves the question, like I did in the initial slide, what is the probability of some random variable taking on a certain value? Now, what did I say earlier? I said, what's the probability that's going to rain? None of us really are experts on that, although my wife seems to be an expert on predicting the weather. But even if you turn on the television or you go online, the weather people, they're not perfect, but they do deal in probabilities of the front coming down and the humidity, and I'm making this stuff up because I don't know anything about the weather. But notice what I gave as an example earlier. What's the probability that the board of directors is going to declare a dividend of $1.35? Now that has some meaning for us as financial analysts. So a discrete variable, the probability function uses the lowercase p of x. A continuous variable uses the notation of f for function of x. Couple of key properties. Of course, those probabilities have to be between 0 and 1, and the sum of all probabilities then must equal 1, right? Let's go to my simple weather example. It either rains or it doesn't. If the probability of it is going to rain is 20%, then the probability that it doesn't rain is 80%. And there's the notation for the cumulative distribution function. Just a really super quick example here. Look at in the very middle. Consider a special dividend with 7 possible year-end values. What is that? 3, 5, 6, 9, 13, 14, and 15. So we can write that here as the shorthand version, dividends, and then we're going to open up our parentheses and just put those in there, separated by commas. A lot of times in financial research, if we have way too many numbers as a dividend, we'll probably divide them into ranges. And quickly we could just say something like dividend between 3 and 6, and then between 9 and 13, and then 14 and 15. And we can have greater thans and less thans in there as well. Price ranges, notice we have that in bold down the bottom right. The cumulative distribution function gives us the probability that a random variable is going to be less than or equal to. So let me go back here real quick. With discrete random variables, and if we have a sample that has 7 possible year-end values, we can deal with 7. But remember, with continuous compounding, you have a whole bunch of them in there, right? An infinity and beyond number in there. And so it's much more appropriate to say something like this. What is the probability that the board of directors will announce and declare a dividend that's greater than $1.35 or whatever number I said just a few moments ago? So notice in that second curved arrow point, all values qualifying as less than or equal to the specified value. Now, one of the simplest ways that we can do this is by using the illustration of a tree. So think about this on the left-hand side over there where those 2 lines reach a point. That's the beginning of the tree. And then as we move out this way, we have all the different branches. And we're going to either move upwards or downwards. So we have a binomial path. There are only 2 different outcomes. So the classic example of this is for just flipping a coin. So notice we're standing here and we're getting ready to flip a coin, so we can flip it. It can either be heads or tails, right? This is not super difficult stuff. And then after we flip it one time, we can flip it again, and then we can flip it again. So look out on the far right. There are only 8 possibilities. You can have heads 3 straight times, you can have tails 3 straight times, or you can have, any combination of 1s and 2s in between. So 3 coin flips results in 8 possible outcomes. And there's the probability distribution over there on the right. So just look at the extremes. You have a 1/8 chance of getting 3 heads and a 1/8 chance of getting 3 tails, which then must mean you have a 3/8 of a chance of getting 2 heads or 2 tails or vice versa. Now, let me go ahead and warn you that this tree is going to be super, super important as we move through, especially when we get to level 2. We're going to use this tree to help us understand the binomial option pricing model. We're going to use this tree to put together possible interest rates. We're going to call it an interest rate tree. And then we're even going to use this to price a bond, maybe even more importantly, to price a bond with an embedded option. And we can use this kind of a tree to price lots and lots of derivative securities. So this tree right here, you're going to see over and over again. Now let's go ahead and look at a picture of this cumulative distribution function. And so all we're going to do is just take the 1/8 and add the 3/8 and add the 3/8 and add the 1/8. So as we go up, right, we eventually get to 100%. So that cumulative probability is 8/8 or 100%. And so note this is number of heads down on the horizontal axis. Could be the number of tails as well. Now, remember what I said a few moments ago about asking ourselves, what happens if something falls within a range? So let's go ahead and take a look at a more specific question than we've been addressing previously. So look at the blue box. What is the probability that x will take on a value of either 2 or 3, given that table that we just constructed there? And so the value of 1 is 15%, and then 1 or 2, and 1 or 3, 1 or 2 or 3, and then 1 or 2 or 3 or 4. So we all go up to 100%. What is the probability? All right, so you think about that the value is either a 2 or a 3. Well, there's a really simple way to do this, and I'll hold this down until the note at the bottom. But what we can do is we can determine the probability that it will turn out to be exactly 2. And since this is the cumulative probability function, we need to kind of decumulify. That's not really a word. And so we're going to say just 45 minus the 15. So that gives us 30% chance for the value taking on 2. And then we're going to take 80% minus the 45% for the value taking on 3. And so we can just add the 30 and the 35 to get the probability that this value will take on a 2 or a 3, 65%. Or you can just go from 80 and subtract the 15 and skip the middle 45 there as well. So 65% either way. Probably the note is the best shortcut that you can think of for the exam. All right, how about continuing to discuss a discrete random variable, but let's go ahead and add another word in there. Let's add uniform random variable, which is what we were talking about earlier. The throwing of a die is going to result in a uniform distribution because we have that line, right? What was that? 16.7% of a chance of throwing a 1 or a 2, and so on. So the probability there was 1 over 6, right? And the mean is going to be k plus 1 over 2, and then the variance k squared minus 1 over 12. Now look, that LOS asks us to calculate and interpret probabilities given that discrete uniform distribution function. So I'm not sure if you'll have to compute the mean or the variance, but those are two formulas that you ought to know now, because sooner or later you're going to have to, you're going to run up against an LOS that asks us to calculate those. Look at that last circle point at the bottom. Financial analysts use this uniform discrete random variables when they intend to simulate random numbers where each number is equally, that's important, equally likely to occur. Now, the continuous uniform distribution is virtually identical to the discrete one, but of course it takes on a completely different form, but we're still with this uniform distribution. And so we must establish a lower limit and an upper limit, and that's noted by alpha and beta. And there's the probability density function there, 1 over beta minus alpha. Now look at that first teardrop point. So we have an X and then a little squiggly line, that's called a tilde, and then a U. That U stands for the uniform. And then there's the alpha and the beta. And so what's really important is for us to be able to ask the question, and what did I say earlier? You know, what happens if a random variable, continuous random variable, what's the probability of it falling between two numbers? So look at that boxed equation there. We have an x1 and an x2. We want to know what that x is in the middle. What is that probability in the middle? And that's a super simple formula to remember. So here's a good example. We have a uniform distribution that falls between 100 and 300. So let's calculate two probabilities. Let's calculate the probability that y, that uniformly distributed continuous variable, is greater than 178. And the second part is between 100 and 226. Now, before I hit the solutions page here, let me just try to simplify this for you. Look, we have 100 as the min and we have 300 as the max. So what's the probability that y would take on a value greater than 200? Well, right, it's right in the middle between 100 and 300, so that would have to be 50%, right? So hold off on that thought, and let's go ahead and look at the answers here. So that first question, calculate the probability of y being greater than 178. We're going to take that max value of 300, right, minus the 178, and then divide by just the max minus the min, and that gives us 61%. And then we can do the second one. We can take the 226 minus the 100 divided by the same beta minus alpha, and we get 63%. So let's go ahead and harken back to my original question. What was the 200? So look at the top formula there. So you have 300 minus 200, right? That's 100, and then 300 minus 100 in the denominator, that's 200. So that's the 50%, right? And so a great shortcut on the exam, although I'm not sure the Institute would do this for you. You know, if you were given this question and you were asked to calculate greater than 178, and choice A was 22%, and choice B was 48%, and choice D was any number greater than 50%, you would know that it would have to be the correct answer. All right, how about this LOS? Describe the properties of a Bernoulli random variable. This guy, Jacob Bernoulli, was a fascinating dude. And the reading doesn't give any kind of a history lesson on him. But he lived a super long time ago. And I read something interesting as I was preparing for this, that on his tombstone, his wife put he was an incomparable mathematician. So he did all sorts of crazy math stuff. But of course, what the Institute is interested in is his study on success or failure. And this really lends itself extremely well to what we're trying to study, like success or failure, like a default on a bond or not default on a bond. Now, those success or failures don't have to be a 1 or a 0 outcome. So look at the example we have there. Success could represent any return above 10% on a stock. That would be success. Any return 10% or less would be considered a failure. So notice how this Bernoulli trial, it goes back to what we were just doing with probabilities in our 178 and 100 and 226 or whatever those numbers are. Bernoulli was also the dude who discovered the number 2.7 something, that little e to the x button on your calculator. We're going to go ahead and look at that here in one of our slides coming up. So remember Bernoulli for now, but also remember his name for just a little bit later. All right, so probability of success, there's the theta, probability of failure, 1 minus theta. That makes perfect sense. Now notice the LOS says something like calculate and interpret the probabilities. And so there's our good formula right in the middle there, probability that the uppercase x is equal to the lowercase x. And notice what we're doing on the right-hand side of that equal sign. We're going to take the theta. All right, so there's the probability. What was our probability on that last one? 70%. So we're going to take 70%, and then we're going to multiply it by 1 minus 70%, which is 30%. So we're going to do this multiple times throughout the CFA program. We're going to take a probability, and then we're going to multiply it by 1 minus that probability. All right, so that's the base kind of understanding to figure out probabilities of random variables that are binomial in this case. And then we're going to adjust that multiplied probabilities by some of the counting methods that we learned in a different study session. So we have to raise that first probability to some number, and then we have to raise the 1 minus theta to some other number. And then notice in parentheses there we have the n over the x. So this is the part of the counting of the factorials when we did that in the previous study session. Let me show you what I mean here. Of course, an example proves this even better than some large, intimidating formula. All right, here we have investment bank. Probability that an investment bank will survive a large-scale financial crisis, 80%. So what is the probability that at least 11 out of a group of 12 will survive that particular crisis? So another way of asking that question is, what is the probability of 1 or 0 of those banks will not survive? All right, so depending on whether you go that way or this way. So let's go ahead and work through that example. So n is 12, theta is 80%. So notice we're interested in the probability that at least 11 out of the group of 12 will survive. So that's why in the parentheses we have x is greater than or equal to 11, right? And then next to it we have the 11 or 12. All right, so all we're going to do is we're going to use that formula from the previous page, the previous slide, which is right there. So the factorials, we're going to do 12 and 11, and then we have 80% raised to the 11, and then 20% raised to the 12 minus 11, and that gets us, what is that, around 20 or 21%. Then we need to do the probability of 12, right, because it's 11 or 12, so we're going to have a plus sign somewhere in here. So we do all that same stuff, and we get, what is that, about 6 or 7%. So total probability 20% plus almost 7%. So that gets us up to 27% chance that 11 out of a group of 12, at least 11, will survive this financial crisis. Oh boy, I warned you that we were going to use that tree earlier, and lo and behold, it pops up already. So here's a binomial tree that is going to help us estimate stock price movements. So this is what we do for a stock price binomial tree. We start with the stock price today, and we can observe that. What we then can do is we can say, hey, the stock price is either going to go up or down. So let's just start with 100, right? Today's stock price is 100. And let's just suppose for some crazy reason that the price could either increase or decrease by 10%. So right there with the lowercase u(s), we're going to put 110. And right below it with the lowercase ds, we're going to put 90. So you see how we start at 100, the price can either go up to 110 or down to 90. And then once we hit that path, notice at t equals 1, we call that a node. At t equals 1, we now have two paths. We have two outcomes instead of the original one outcome at time period 0. So we just do the same thing, right? We can have this tree go way out. In this case, just like our flipping of the coin with the heads or tails earlier, we had 3 flips of the coin. Here we have 3 time periods, but there's nothing to prevent us from going out to 3 or 30 or 300, right? I mean, think about what a crazy looking tree that would be. If the CFA Institute gives you a 30-period binomial tree on the exam, go ahead and just pick A and move on with your life. Of course, the CFA Institute would never do that. I'm guessing that reasonable questions would be a 2, a 3, and perhaps a 4-period model. All right, let's go ahead and talk about distributions. Remember, distributions so far could be uniform, right? We had that straight line, but as I said earlier with my James Bond example, those distributions don't have to be a straight line. They can be a curve. And so that's what this normal distribution, it's a curve that looks like a bell, right? So there's the bell-shaped curve. And the cool thing about the bell-shaped curve is that if you put a mirror right in front, can I do this right here? Can I go all the way into my slide? If you put a mirror right there in the middle instead of that line, you'll look at mirror images of each other. So this is a symmetric distribution. So what's to the left of the center point and to the right of the center point are mirror images of each other. And so as a quick example, if I were to collect data on yields on callable bonds that are double B rated, maybe I could get 100 of those things. If I calculate the mean, I put that right in the middle. So there's the mu right in the middle. Now that would be a population. Mean, so that would go right in the middle. And then I can go on either side, and we'll see this here in just a second, by the standard deviation. But here's a couple of things that you need to know. What does this ask us? Key properties of the normal distribution. So the first property was the symmetry, right? Second property was you can use mean and standard deviation. And part of that is that the mean and standard deviation, of course, for a normal distribution completely describes that distribution, which means look at property 2 and 3 at the bottom. There is no skewness. There's no skewness to the right or skewness to the left. So remember, skewness of 0 is a key property of the normal distribution. And kurtosis, which is the fourth moment of the distribution, we say that it is normal. We don't typically say kurtosis equals 0. We say it has normal kurtosis. So distinguishable properties, mean and standard deviation, first 2 moments of the distribution, completely describe it. Skewness is 0 and kurtosis is normal. A couple of other key properties, the mean, the mode, and the median, they're all equal. Median, they're all equal, so they go right there under the mu, right? If you have two variables, this is really super important. If you have two variables that are normally distributed, in this case we have an x and a y, and if you combine them, the resulting distribution will be normal as well. And then at the bottom there's the notation for what we've been talking about all along, probability that a value lies between A and B of a continuous random variable. All right, there's our picture of the normal distribution. There's a bell-shaped curve, right? Right in the middle is the mean. But what we can do is we can add a standard deviation to both sides. So notice to the right of the mu, there's a plus standard deviation. So that's the Greek notation for the letter S, right? That's sigma. And then to the left of it is a minus standard deviation. And so if you add and subtract a standard deviation from the mean value, what happens is that 68% of all outcomes will fall within that range. I mean, this is really an unbelievable result. And this goes back to something that I'm betting that you learned this in your undergraduate statistics class. It was called the central limit theorem. And this was developed around the time of my favorite statistician, a dude named Chebyshev, who did a bunch of this stuff as well. And there was another guy named Lyapunov who did some other crazy work. But these, they combined mathematics with statistics and standard deviations. And so think about this. What did I collect data on? I collected 100 yields on callable bonds, right? Well, if my mean is, let's say it's 10% and my standard deviation is 1%, what that means then is that 68 of those 100 yields on those callable bonds will fall between 9 and 11%, right? Plus one standard deviation and minus a standard deviation. And then, of course, you can do this as you move out to 2 standard deviations, it's 95%. And out to 3 standard deviations, it's 99 and a little bit more percent. And so that's super important for us to try to manage risk, right? If we have a security that has a low standard deviation, we're able to more accurately predict what that variable is going to be within some kind of a range. If we have a standard deviation, let me pick a crazy standard deviation. Let's say it's 100%. If you have a financial security that has a mean of 10%, and a standard deviation of 100%, you have absolutely no idea what's going to happen to that stock over the course of the next period. I mean, that's range. Can you guys see all the way out here? My arms are way out here. All right, let's look at the LOS about multivariate and univariate distributions. All right, so univariate, uni meaning one, so that's not surprising for you to read that, involves just one random variable. A multivariate distribution, a group of related random variables, particularly if the individual variables follow a normal distribution. So we need to know about means and variances for both univariate and multivariate, but they become more and more important in the multivariate distribution because of how they relate to each other. And that's why we have correlation at the bottom. And we talk about correlation all the time throughout the CFA program. Correlation, remember, measures the strength and the direction of a relationship between two variables. All right, how about if we go ahead and calculate the probability that a normally distributed random variable lies inside a given interval. All right, so this is super important. We're going to do things like prediction intervals and confidence intervals. Now, we don't get into all of the details here in this reading, but we will at some time in the future. And so what we're trying to do, look at that second teardrop point. The precision or accuracy of the estimate depends on the width of the interval. So if we go back to, let me go back to this one here. If we assume a normal distribution, we may or may not have a normal distribution. It's going to depend on what does it say back here? The width of the interval, which depends on, right, the standard deviation of that underlying variable. All right, so here's a good summary page here of what we did just a few moments ago. 50% of all observations fall within plus or minus of 2/3 of the standard deviation, then 68% one standard deviation, 95% two standard deviations, and then 99% three standard deviations. Now look at the last teardrop point. The reading doesn't get too terribly technical here, but we will get technical in the future. Precise intervals, especially at the 95 and 95% level of confidence, will be not just 2, that's an estimate that we have in the gray box up there, but 1.96 for 95% and 2.58 for 99%. Those 1.96 and 2.58, they come from the z-tables, which we'll do on this slide. All right, so let's go back to the beginning of statistics. If you are having a conversation with your friends about football, and one of your friends is a gigantic Tom Brady fan, and he says something like, "Oh, Tom Brady's going to throw 5 touchdown passes this coming Sunday," and you say something like, "Wait a minute, that's the craziest thing I ever heard. Nobody throws. Who does he think he is? Peyton Manning? He's only going to throw 2 touchdown passes this week." So what was that? 5 minus 3 or 5 minus 2 equals 3. So you have a 3 there. But what if you do this over an entire season, and it's 103 and 100 for the entire season? You still take 103 minus 100. You still get 3 in the numerator. Well, what econometricians do over the years, and of course, as good financial analysts, we are becoming near econometricians, not pure econometricians. But what we do is we standardize that random variable. So notice z there. We divide by the standard deviation. So what did I say? 5 minus 2 equals 3. And 103 minus 100 equals 3. Those 3's are not the same number. What we need to do is standardize them, because one was one game and one was an entire season. So in order to standardize something, we just divide by the standard deviation. So this z to the left of the equal sign, it is a normal distribution, and it's standardized. So this is super cool. It has a mean of 0 and a standard deviation of 1. So no matter what you're doing, whether it's touchdown passes or yields on callable bonds or operating cash flows cross-sectionally, it's going to have a mean of 0 and a standard deviation of 1 because of this standardization process. And there it is. So we have x, which is the kind of the sample mean, minus mu, which is kind of the population mean. So we're always subtracting with z. And that's the result of 2 researchers having an argument, or a researcher having an argument with his or her sample and the population. And so this disagreement means there's going to be a minus sign in the numerator, and then we divide by the standard deviation. So we can calculate, let me go back here real quick. We can calculate that z for any kind of a random variable. And then in order to get the probability, we need to look this up on the z table, which, here, let me go back here real quick. One thing I didn't say about this normal distribution is that if we go 1 and 2 and 3 standard deviations on either side of the mean, we can get 68%. So there's probabilities embedded in this bell-shaped curve. And actually, if you do this, don't ever tell your econometrics professor that I said to do this, but if you take a ruler and you go from the horizontal axis all the way up to the top of the curve, we put that in there as the mean because that's the highest ruler, that's the highest distance, right? So that outcome has the highest probability of occurring. And so as you move out, the ruler length becomes smaller and smaller and smaller. So the distance between the horizontal axis and the bell-shaped curve is the probability of that actual event occurring. Now, of course, we don't use rulers, we use the z-table. So that's what we're doing here. So I want you to think about this. This table is really just a ruler. We're measuring the distance. We're measuring, all right, is it 4 inches or is it 12 feet or what is it? But we can't use the ruler. We use the z-table to get a probability. And so before we get to the example, let me just give you a quick lesson in how to read this table. Suppose we got a z of 2.5. So we got the mean, we got the standard deviation, we compute 2.5. So all we do to read this is we run our fingers, no, did I say 2.5? How about 0.25? Run our fingers down to 0.2 and then run our fingers over to 0.05 because 0.2 and 0.05, that equals 0.025. I'm sorry, 0.25. And then we get the intersection of those. And what's that number? 5987. So that's the probability associated with whatever we were doing, Tom Brady touchdown passes or yields on callable bonds, 59.87%. So let's do a real live finance example here. Look at the bottom. Portfolio has an expected mean return of 8, standard deviation of 14%. Oh, here's a great question. Going back to what we've talked about over the last 15 minutes. What's the probability that the return falls between 11 and 15%? So what we're going to do, and before I give you that answer, let's go back here to the bell-shaped curve. Think of 11% being somewhere on there. Think of 15% being on somewhere. And so we're getting out our ruler and we're going to try to measure the area under the curve in between those two numbers of 11 and 15%. And so that's what we're doing right here. All right, so look at the purple dot. The z value corresponding to 15%, that turns out to be 0.5. The z value corresponding to 11%, that turns out to be 0.21. So we've circled those here. So 0.21 is 5832. And 0.5 is 6915. So all we have to do is subtract those two and we get 10%. So what was our question? Probability that the return falls between 11 and 15% is 10.83%. Now, whether or not you've had lots of history and experience in using z-tables, or whether this is just your first experience in this kind of endeavor, you have to admit that this is super cool. You know, going back to Chebyshev and Bernoulli, all these dudes in the old days, they really created an environment and a tool so that we can answer these important questions. Look, when I teach my investments classes, both undergraduate and graduate levels, we do this in the context of the policy statement. So I have my students create a fictional client, and then we do all this stuff, a risk objective and a return objective, and then I ask them questions like this. Okay, what's the probability that the return on the portfolio that you're creating for your client falls between 11 and 15%? And we can come up with this number, 10.83%. Man, that deserves a high five. Did you happen to see on the red zone this past weekend in NFL football, some dude caught a touchdown pass and he did a backflip in the end zone. You know, he just stood there and jumped up. This is what you should be doing here on your seats. Backflip. No. If I did that, I'd probably break my neck or something. So let's pretend that we're doing a backflip. Let's just give each other a high five. All right, remember I said this early on in the slide deck that we're going to do lots of stuff on distributions and random variables, and then we're going to hit some section where we're going to be able to ask about our, what did I say earlier from the reading, right? Informed investment decisions. Now that's where we're starting here. So this LOS asks us to define shortfall risk, safety first ratio, and goes back to Roy's safety first criterion. And I'm so glad that this is known as Roy's safety first criterion. You'll hear me talk about Harry Markowitz and his efficient frontier many, many times throughout lots of these recordings. And when Harry Markowitz received his Nobel Prize in economics, he did mention Roy as being right there alongside of him, although Roy never did win Nobel Prize in economics. So this is super important stuff. Now remember, there's a bell-shaped curve. Remember what we did earlier is that we started in the middle, right? We called that the mu, and we added and subtracted a standard deviation, right? And then 2, and then 3, and then however we got to. But now shortfall risk, we're just concerned with the left side of the tail. We want to know, what is bad news? What is the probability that we're going to get bad news? And so my students, when they craft this policy statement, they'll come up with a return objective. Maybe it's 8 or 9 or 10%. And I'll ask them, I'll say, okay, if your client generated a return through your advice of 6% or 4% or a -2% or something less than that return objective, how would your client feel? And the students always say, well, they're not going to be very happy with me. Of course they're not going to be happy. But what we need to do in all of our studies here is identify a benchmark or a minimum return. So that's what shortfall risk does. It says something like, look, what happens if we hit this minimum return? So my client might have a 10% return objective, and the minimum return might be 2%. And so, boy, we ask ourselves the question, what's the probability of generating a return less than 2%? So look at that second teardrop point. Shortfall risks are downside risks. Downside economic risk. So that we're doing standard deviation here. And so this means total volatility of a financial asset. Now notice we slightly changed the notation. Instead of the mean there right in the middle, we have the expected return on the portfolio. Expected return. Why do we call it the expected return? Are you ready for this? Because it has the highest probability of occurrence. And so notice that minimum return, that benchmark return, is somewhere to the left. And all of those vertical blue lines, that's shortfall risk. So we want to know what that probability is down in that left-hand corner. So we use Roy's safety first criterion. All right, so all we're going to do is take the expected return on the portfolio, which is the mean, and we're going to subtract that minimum portfolio. The reading uses the notation R sub L for the threshold level of return, and then we're going to divide by the standard deviation of the portfolio. So you shouldn't be surprised by this. I mean, this is clearly not a z-score, but we have two things in the numerator. We're subtracting the two, and we divide by standard deviation. So if we assume this normal distribution, then the optimal portfolio is the one with the highest safety first ratio. And that should be perfectly obvious. Moving on to lognormal distributions, we're going to have lots of conversations in level 1 and level 2 where we make the assumption that the relationship between two variables is linear, and this occurs throughout finance and economics. But sometimes the relationship between two variables is, and this is going to be my term here, this is not any kind of statistical or economics term, I'm going to call them nearly linear. And so what do you do when you have nearly linear relationship? Well, one of the things you can do is you can transform one or both of the variables into their log form, and they will form a lognormal distribution. So you need to get in the habit of being aware that there are normal distributions and then there are lognormal distributions, in which all we do is take the natural log of the random variable, and then that relationship could become linear. But what the reading emphasizes here is that once we go ahead and transform a variable into its log form, we take away any of the negatives. So look at the picture there of a lognormal distribution. It starts at the origin, so that's 0. So it removes the possibility of negative values, which sounds an awful lot like it is receptive to analyzing stock prices, because stock prices can never take on negative values. Now let's get back to Bernoulli, and I want you to forget about everything at the top of the slide. I want you to skip down to the bottom, and then we'll go back up. I want you to visualize a scenario under which you have a stock price in time period 1 of 100 and a stock price in time period 2 of 110, right? What's the holding period return on that? That's 10%, right? And there's no, you don't even need your calculator for that. Start at 100, you end up at 110. But what if instead of assuming annual compounding like we did in that example to get the 10%, suppose interest is compounded continuously during the course of the year. In other words, it's compounded at every instant of every single minute of every day, of every week, of every month during, this goes back to the Buzz Lightyear and infinity and beyond. Well, to wrap our arms around this concept of continuous compounding, all we really need to do is hit our ln button, right? Take the natural log of 110 over 100, and we get 9.531%. So a 10% annual rate of return translates into a 9.531 continuously compounded rate of return. And continuous compounding is going to be super, super important when we get to option pricing and some other derivative pricing. So this is a concept that you need to know. So you might as well learn it now so that you can apply it sometime in the future. Now, of course, the next question is, how do we go from a continuously compounded rate of return into an annual rate of return? And here's where we have Bernoulli to thank. He was the one who came up with this number, 2.7183, and then there's a whole bunch of numbers out there as well. That's the little e raised to the X button on your calculator, and the E stands for Euler. You would think that it would be a B. You would think that he would have given it the letter B, but he chose E for Euler because this dude Euler was another Swiss mathematician who was quite an influence on him. So all we need to do is put 09531 in the calculator, hit the E to the X button, subtract 1, and there's the 10%. All right, so that math example ought to give you a good introduction to what we're doing above. Continuous compounding, time is viewed as continuous. So there's the effective annual rate, e to the x minus 1. That's what we just did down at the bottom. And then continuous compounding, all we do is take the natural log of 1 plus that holding period return. So that would be the natural log of 1.1, right? That's 110 divided by 100. All right, moving on to different types of distributions. So what did we do? We know that Z distribution was normal. But there are other distributions that are almost normal, but not quite normal. But boy, we really wish that they were normal, but they're not. But under some conditions, they become normal. So that's the nature of this student's T distribution. So notice there's the normal distribution. And then there is the student's T distribution, which is less peaked and longer and heavier tails. So it's a nearly normal distribution. But here's the thing. As the number of observations in the student's T's sample, as that increases to infinity, the T distribution essentially becomes the standard normal distribution. But that's why we have a Z table, and that's why we have a T table, because we have to adjust for the degrees of freedom, which is n minus 1. Here's what the reading tells us. The t-test is used for differences between two means, correlation significance, as well as in a future reading where we'll look at regression analysis. And so think about this. Whenever you have a sample that's 30 or less or so, you're probably going to use T. If you have a sample of 1,000, you're going to use the Z. And as you go from 30 all the way up to 1,000 in your sample, that student's T distribution becomes more and more and more like a normal distribution. How about a chi-square distribution? So here, let me go back here real quick. Means, that's what we're doing with T distributions. We like to do means, however those means, those averages are given to us. So it makes sense then that we need a distribution for standard deviations or variances. And that's what the chi-square distribution is. And that's why the CFA Institute spends a little bit of time on that log-normal distribution that we talked about just a few slides ago. So look at the picture of the chi-square distribution. You know, it starts at 0 and it has some skewness in there. So of course that's not a normal distribution. Of course, we need to be concerned about the degrees of freedom. And so notice that, look at the third point, the property. The sum of the squares of k independent standard normally distributed random variables. So therefore, again, chi-square is non-negative. That's important. So as those degrees of freedom increase, the shape of that chi-square distribution, you know, so the hump, you know, it's less and less to the vertical axis. It goes out to the middle, and those tails become more and more like a normal distribution. And so notice what we have in purple. It's used as the test of variance for normally distributed populations. Now suppose that we want to test multiple populations, variances, and that's what we have, the F distribution. So let me go ahead and give you the punchline. Look at the bottom right in purple. The F test is used as a test to determine if there is a statistical difference between two variances of two populations or samples. You know, going back to my example of yields on callable bonds. What did I say? Double B. Suppose I picked another sample of AAA rated bonds. Well, I mean, they're probably not going to have the same mean, so I could do a t-test to see if their means are alike, and they're probably not, but I need to use an F-test to see if their variances are alike, and they're probably not as well. So that's what we use, the F-test. But because we have two samples or two populations, we have degrees of freedom in the numerator and degrees of freedom in the denominator. So remember that with the F distribution, and you'll get that when we hit the analysis of variance discussion in a different reading. Once again, look at 4 as degrees of freedom for both. I have to go both the numerator and the denominator. It approaches a normal distribution as well. Let's go ahead and look at this last LOS and finish up quickly. Describe a Monte Carlo simulation. Let me give you this example. Let's suppose that we're trying to price a 3-year bond, and that bond has $100 interest payments at the end of each of the next 3 years, and it has a $1,000 par value payment at the end of year 3. Well, we could just get out our financial calculator and we could go ahead and hit our time value of money buttons and find the price or the present value of that bond. All right. We don't need Monte Carlo simulation to find the simple price of a simple fixed rate bond. But let's suppose that we're trying to price a structured note. Oh man, wait till you get level 2 and we talk about structured notes. And let's suppose it's still 3 years, but instead of 100, 100, and 100, let's suppose that the payments are quarterly. And let's suppose that those payments depend on, which means they're not fixed, that they depend on the dividend yield of some big company's stock out there. So you're going to get 4 payments a year, right? So that's a total of 4 payments times 3. So that's 12. Instead of having 100, 100, 100, you have something, something, something. You don't know what they are, right? You don't know what they are because you have to wait and see what the dividend yield of this big company is. You use that dividend yield to compute the interest payment. All right. So this is called risk and uncertainty. Well, you might be thinking, wait a minute, Jim, let's go back and do our interest rate tree or just some kind of a tree, and let's go up and down and up and down. But you need to think about this. How many branches are going to be on that tree? There's going to be lots of branches. And then let's suppose that the maturity payment, which was $1,000 in our early example, let's suppose that that par value payment depends on the performance of a mortgage-backed security. All right, so let's combine all of this stuff here. We need to do probabilities times all these different dividend yields for this particular company, and then probabilities of mortgage-backed securities. So we need to do probabilities of things like prepayment risk and financial crisis risk, and what is the risk of people just deciding not to pay their mortgages. All right, you see this structured note. I mean, that's kind of a crazy structured note that I described, but it lends itself perfect to a Monte Carlo simulation. So look at the illustration we have down on the bottom right. We're going to start at time period 0. And then what we're going to do is we're going to input all of the variables. So what do we have? Dividend yields and mortgage-backed securities, right? And what we're going to do is we're just going to change each variable at each different node. Think of it as each different node on that tree. And then we're going to calculate the price. And we're going to do this. Notice it says on that first arrow point, we're going to run this many times. Hundreds of times, thousands of times, maybe even tens of thousands of times. Look at the second arrow point. Very useful when the number of random variables is too high. So you can't do an interest rate tree. You can't use your time value of money buttons. You can't even use Excel. It's very complex. So you have somebody who's way more technical and smarter than I am to put together an algorithm which will change each variable and then recompute a price. Change it again, recompute a price. Change it, change it, change it. Do this 1,000 times. So Monte Carlo, estimating risk and return, valuing complex securities like a structured note, and financial modeling. But of course, you're saying to yourself, wait a minute, Jim, you always teach us this, marginal cost, marginal benefit. Well, look at the second block point there. That specially designed software that may be expensive, we're not going to be able to get exact results. We're going to get a mean, right? We can get a mean and a standard deviation. We can do all that kind of stuff. But this complexity may lead the financial analyst to some inappropriate or even worse, inaccurate conclusions. I think that takes us through. So think about this. Group these into 2. Distributions and random variables, and then financial decision-making helpful tools.